Hello guys, Cyprien here from FEFO, and today we'll talk about a very interesting topic, the Lattice Boltzmann Method. So this is a method used to calculate CFD simulation. And usually, if you search about this method online, you'll find a lot of complex equations and a lot of theory. And the purpose of this video here is really to make everything simple to understand. So I will not go very deep in the equations. I will go more about the concepts and teach you, what this Lattice Boltzmann method is compared to the traditional CFD methods, what the advantages are, and I'll show you a few examples of how you can use it, and basically this should be a very interesting presentation for you if you have no notion at all about what the Lattice Boltzmann method is. So thank you for watching this video. If you think this is important knowledge, please click the like button. Thank you very much. So all this video is based on an article that was written by a friend of mine, Dr. Nicolas Maquignon, who is a specialist on the LBM method. So he's done a PhD thesis on it for liquefied natural gas, and he wrote this article on my blog like 5 years ago. So and we did together some introduction to the LBM method. So all the knowledge you'll have in this video today was coming from this article. So if you want to refer to this and see everything in text format, just go to this page and have a read about this article. Also, what I want to say is that if you want to contact Nicolas, please, his email is here on the slides. He's very friendly and he likes to talk about the LBM method. Okay, so let's go into the actual presentation. So the Lattice Boltzmann is a kind of a new method which is used for CFD, and it attracts many researchers and engineers mainly for two reasons. So the first one is that it's a code which is multi-physics, so you can easily enough integrate more physical behavior into the code. So we'll talk a bit more about why later. But basically this allows you to simulate turbulence, acoustics, phase transition, fluids with thermal interaction, all of that much more easily and with better accuracy than like more traditional CFD methods. And the second reason is that it's a high performance computing code, so it's basically designed for that. So, and this is due to the method of the Lattice Boltzmann. So that's what we'll describe later in this presentation. So it goes really well on the GPU, and it can be scaled easily. Meshing is also faster because it's using a grid. So, right now we are in the era of putting everything on the cloud, so you can go for much higher problems and more efficient type of resolution with more accurate results if you use the Lattice Boltzmann method. Now the first concept you must understand to understand what the Lattice Boltzmann method actually is that there's a stark difference between microscopic and macroscopic scales. If you look at water in a macroscopic view, well, you see a medium which is continuous. So, you see water with certain material properties, density, velocity of the water, and it's like a material, and this is described by the famous Navier-Stokes equations. But if you look closely at what is inside a drop of water, well, what you have is molecules, right? So you see particles which have certain quantities, and those density and velocity of those particles take a whole other meaning. So what about general CFD programs? Well, the most CFD programs that you will find out there, they are solvers that are numerically integrating the Navier-Stokes equation, which are macroscopic equations. And then they use some methods that can be finite difference, finite volume, or finite element methods, and of course a graphical interface to solve all of that. But LBM is different, and we'll see why. So if you have never heard about the Navier-Stokes equations, well, let me refresh a bit your memory. So the Navier-Stokes equations are the most famous equation in fluid dynamics. So they describe the temporal and spatial evolution of density, momentum, energy, and they are what basically are used to calculate everything in the traditional CFD solvers. So they can be solved using Lagrangian or Eulerian frameworks, depending on the problem to study. Said more simply, it means that you can either look at the fluid going in the square from a fixed position, or you can look at it from a moving position with the particle of the fluids. And in those equations, density and velocity are continuous macroscopic variables, and this implies that they can be described with continuous functions, and also that we can measure them with the appropriate instruments at the human scale. So this is what the Navier-Stokes equations are. So how do you actually measure density, mass, and velocity of a fluid? Well, there are several methods, either simple or advanced. A simple method would be to use a dosing glass, and then you can measure the mass, you can measure volume, and then you get the density. So that's what generally we do in college when we don't have the most advanced tools. And if you think about the advanced methods, well, you have sophisticated method like particle tracking velocimetry, which allows you really to study the velocity field of a fluid. And then you can add pressure sensors that can inform you about the pressure at some strategic points. And those are all very cool and very expensive equipments that you will find in R&D labs. I still remember my fluid mechanics course back in the days where the professor was so proud of his equipment and showing us all those nice looking pictures of fluid fields that he calculated. It was really, really interesting. But, all this is different when you go into the LBM method, because you cannot measure those same quantities macroscopically in the same way. Why is microscopic scale so different? Well, if you look at a drop of water, like you have here in this picture, it seems that globally the current way we think is available in the macroscopic state is much more different when you study the fluid in the microscopic scale. So the dimensions there, we can see the particles. So the apparent continuity of the scale is broken. And you have to find another way to get back those macroscopic quantities like density, velocity, and all of that. And this is what we'll talk about here in this presentation. So I'll tell you how to do that. But first, maybe a question that you're asking yourself is, why the heck should I care about the microscopic scale of fluids molecules, right? We have been using these Navier-Stokes equations for so many years right now, so, why are we bothering with the microscopic scale and all this? Well, the first answer to that is, if you look at a fluid in a microscopic scale, it is an ensemble of molecules. So they have an unexpected behavior, unpredictable behavior, and we cannot ignore that. So, it's very important to establish the link between micro and macro scales, because it improves our understanding of the fluid behavior, and we can use that to learn new things, to improve our knowledge, and to improve with the method we know, to find more accurate and more efficient ways to see the world and to calculate things. And that's exactly what the Lattice Boltzmann method is doing. So what are the big problems with the microscopic scale? Well, if you look at a fluid domain in macroscopic scale, you can see the velocity, right? You can see the water moving in some direction, so you can visualize it with your eyes. But if you look in the microscopic scale, it looks like the atoms are going everywhere in every direction. So how do you define the velocity of the whole domain when everything is seemingly very chaotic? So how can you define a density when you have large vacuum surrounding the molecule of the fluid? How can you define this velocity when they are going everywhere, like I told you? And what's the link between the movement of the particles and those observable properties of the fluid? So those are the questions that the brilliant Austrian physicist Ludwig Boltzmann tried to answer. So he's the first one who established the links and the equations that led to the Lattice Boltzmann method. And if you remember a bit your physics classes, he's also the first person who made the link between the second equation of thermodynamics, and showed that this could be explained using mechanics and the movement of particles. So everything links together. He was a person who studied the movements of the particles and gave us a lot of answers at the macroscopic scale. So in the remaining of this presentation, we'll talk about some of those discoveries and this link between the macroscopic and microscopic and those properties as well. So here what we are gonna be talking about in this presentation in the next slide. So we'll first talk about the study of a gas at steady state, and I'll show you how to find out the density, the velocity, the temperature, and the kinetic energy, and how those variables relate from microscopic to macroscopic state. So after that, you should have much better understanding of this relation between microscopic and macroscopic. In the second phase, we'll talk about the LBM equations. So where it's coming from, we'll talk about the phase space, the distribution of particles, and all of this. And in the third phase, we'll talk about the algorithm of the LBM lattice, and I'll show you a very simple pulse example. So let's start with this study of gas at steady state and zero velocity. So always start with steady state. So think about some air at rest in a room. What do you see? Well, nothing, right? At the macroscopic level, you see nothing. But if you look at the microscopic level, you see basically everything except a steady state. Particles are moving everywhere, everything is in motion, so there's a lot of movement in the microscopic scale. So the first quantity we'd like to find out is the density at microscopic scale. If we look at those particles, they are in relative motion and in this room. and it looks like it's completely disordered and completely random, but appearances are often misleading. So this apparent particle chaos actually hides information about the macroscopic properties of the fluid. And I'm starting with density because it's the easiest quantity to calculate. If you think about a volume of air with a sufficiently large amount of particles inside it, so you can define a density by simply counting the number of particles. So the density will be equal to the mass of a particle multiplied by the number of particles inside the volume, and then divided by the total volume of the room. So I think it's easy enough to understand. So we are not taking into account the shocks between the particles here, and they are in other case considered as hard, elastic, and they have no effect on the mass of the particles. And this is because within the limit of the Newtonian classical physics, the mass is prevented during the collision of particles. Now let's talk about the next important microscopic quantity, which is the velocity at microscopic scale. So if we assume that the velocity vector of a particle can point in any direction, this also means that there is no special direction for the movement of a particle belonging to a fluid at rest. And this is due to the fact that the geometrical space has the same properties in any direction. So in other words, it's isotropic. And this property is what is responsible for the fact that the speed vector sum of the particle is 0. So this is called the isotropy assumption, and basically this zero velocity vector sum is the velocity we measure at the human scale. So this explains why a fluid at rest we measure zero velocity, but we have a lot of disorder at the macroscopic scale. And to summarize simply, the isotropy assumptions means that we have the same probability of a particle moving to any direction, and so the macroscopic velocity is 0. So if you want to see a mathematical demonstration of that, there a bit more detail on the article on the blog, so you can go there and you'll see exactly what, why this isotropy assumption leads to the zero sum of the zero vector sum. Now it's very important to understand difference between this sum of this vector sum, which is null in total, whereas the average velocity magnitude is not 0. So if you think about 3 particles only, it's a bit more easier to visualize. So think about those 3 vectors going in 3 different directions. What is basically null is the vectorial sum of those 3 vectors. So this is null. But if you take the magnitude of the velocity for each of those particles and you make an average of that, this is not 0. Yeah, so maybe it'll take a minute to kind of get to understand this. It's not very intuitive at first, but this is one of the key things to understand here. And because this mean, velocity is not 0, we can get out of that also the mean kinetic energy. And here you have the formulas on this slide. So this is the average velocity magnitude, which is basically the sum of the magnitude of all the velocities divided by the number of particles. And you have the mean kinetic energy, which is 1 half of the mass multiplied by this sum, and there is a square here for the velocities. So if we look at air at 20 degrees Celsius, and you'll see that I'm mentioning temperature because it's important, and we look at the velocity of the particles, we see that there is this mean value of velocity. So for air at 20 degrees Celsius, it's 400 meters per second. And there is a distribution of velocities inside all those particles. So we'll see where it comes from a bit later. So the curve, which is shown here, shows the distribution of velocity magnitude within a volume of air at rest and at a certain ambient temperature. X represents the speed intervals, and Y represents the percentage of particles within a certain range of speed. So we cannot really pinpoint the exact velocity of each of those particles one by one. But we can do is we can say there is a certain probability that a certain amount of particles within this range will have this kind of velocity magnitude, and that's where there is a link between probabilities and physics. So you can write a probability function when for a certain particle to own a certain velocity magnitude within a range A to B. Now let's talk briefly about the temperature. Why did we introduce the temperature? It's because there is a link between the notion and temperature and the average velocity of the particle. And this is because temperature is highly related to the velocity of particles. You can basically, at the microscopic level, imagine that temperature represents the vibration of those atoms. So more temperature increases, more those particles vibrate strongly, and they will enter into more faster shocks or something. So this is basically temperature has an impact on the velocity curve and probability that I talked about. So this is kind of a representation of this concept of the temperature has an impact. So on the left you have 20 degree, on the right you have 40 degree, and you see that distribution of temperature is wider, and it's centered around 600 meters per second instead of 400. So I kind of reduced the scale of second picture so that it matches the scale of the first one. So and knowing about this distribution speed lead us to the distribution of energy in the fluid. So if you don't know what kinetic energy is, here's a very quick reminder about it. Kinetic energy is the energy that something has due to its mass and its speed. So think about a bullet going out of a rifle or a gun. It has a certain large energy, which is responsible for all the damage it could cause when it encounters an obstacle. And the energy of the bullets comes from the chemical energy that was stored in the gunpowder. So energy from chemical is transformed into this kinetic energy that gives it this velocity. So the energy and the velocity, the kinetic energy and the velocity have a direct, relation. And Boltzmann is the one that told us that for a monoatomic gas, this speed energy is called kinetic energy, and he has established that there is a link between temperature and the kinetic energy of the particles, which is in function of the square of the velocity, and you have this constant, the Boltzmann constant. So this KB is a constant called the fundamental constant, Boltzmann constant, and EC is the internal microscopic energy that contains the energy of the particles. So if you try to use this formula for some argon gas, you'll find a mean speed of 427 meters per second, for example. Now we still need to make the link between particle position and particle velocity. And if we think about the mean energy, which is fixed, like I just told you, but the problem is that all the particles on either thermal gas don't necessarily have the same kinetic energy, right? So you have a range of particles, you have velocities which are distributed around a mean value, so you have this kind of distribution of kinetic energies. So to deal with this problem of velocity magnitude distribution, there is another assumption which is done on the kinetic energy. So what we do is that we say that a particle can have any kinetic energy as long as the mean kinetic energy of all the particles allow us to reconstruct a physical coherent macroscopic temperature when summing over all the particles. So that's where we see that the temperature is very important to the coherence of this kinetic energy. And finally, this is what leads us to the expression of this distribution of velocity magnitudes. So if we consider that each particle individually has a velocity according to an individually indeterminate probability law, then we can use a theorem called the central limit theorem that teaches us that for a large number of those particles, distribution law that is globally applied is the Gaussian normal law. So we can that allows us to write this distribution of the speed magnitudes according to the normal law in this way. And this distribution is also called the Maxwell equilibrium distribution, which is valid for perfect gas. So let's talk about the parameters you see in this equation. So the Rs is the specific gas constant. T is, of course, the temperature. Small e is the microscopic velocity. And U is the macroscopic velocity. So you see that you directly have a link between macroscopic velocity and microscopic velocity in using this distribution. So when the previous red and green curves were drawn, this formula was used with U equals 0 for a fluid at rest. Okay, now we did the link between microscopic and macroscopic. So we talked about density, velocity, kinetic energy, and all that. And what you should remember about this is basically the 4 points here. So for a fluid at rest, the vectorial sum of the velocities is null. So this comes from the isotropy hypothesis. Then at the microscopic scale, each particle has a certain velocity which is not null. And this velocity is linked to kinetic energy, which is also linked to temperature. And finally, we can get those the velocity from this Maxwell equilibrium distribution for a perfect gas. Now we talked about the first point, the study of the gas at steady state. Let's talk now about the LBM equations. So to talk about LBM, we need to introduce the notion of phase space. So you know the classic coordinate system with Cartesian system x, y, and z. Well, the phase space is a space in which you have to add more than those three coordinates, and it is necessary for the Lattice Boltzmann method. And the reason is that the normal space isn't sufficient when we come to description of particles. We've seen how important the velocity of the particles is. So the macroscopic property do not only depend on spatial distribution of particles, but it also depends on the speed distribution. So that's why in this coordinate we have to also integrate the speed distributions and the time in some way. So the phase space correspond to the gathering of geometries and velocity spaces. And I'll show you in a few slides what it looks like when you discretize it. But first, let's come back to the notion of steady state, because we've studied the steady state of a gas, right? So what if we are not in steady state? And generally, you know, a gas is not in steady state. It's moving, right? Even macroscopically. So how do you consider that at the microscopic level? So now we have the steady state distribution thanks to the Maxwell distribution. However, the study of fluid rarely summarizes to steady state. So we have to introduce something new to study the properties of the material which has out of equilibrium, and for that we introduce something called the distribution of particle out of equilibrium into the phase space. So if you give a name to the distribution of particles, we call that a function f, which is function of x, small e, and t. So x is the position of a particle, t is the velocity, and e is the velocity, and t is the time. So this corresponds to the probability for a particle to be at position x and to possess a velocity e at time t. And this function is very important to get to the LBM equation. So to get to LBM equation, we use a method that is actually pretty common, is just to make a differentiation of the particles that are moving, and we remove from them the particles that are in steady state, right? So if we are low Mach number and in absence of collision, we can take the differential of f, and we know it is conserved, so it is equal to 0. So we can thus deduce the equality that you have here on the screen, the first equation, which is x plus the function f of x plus a small x, e plus a velocity, which is dx on dt, it's a derivative of the position, plus t plus delta t, and we remove f x e t, and we can use a Taylor development to basically reduce this equation into the term you see at the bottom of the page. So this gives you this expression equal 0. So this leads us to this equation. When there are no external forces, we have the differentiation of f along t plus small e multiplied by the gradient of f along x equals 0. And if we have collisions, we can demonstrate that this equality must be modified by taking into account the variation of the probability distribution in the phase space. And we can add to that a second term, which is called the collision operator. So I will not explain about this in detail because it's very complex. But you have this expression now, and this is the LB equation. So this is it. We got to the Lattice Boltzmann equation, which is, as you saw, the first term and the second term, which represent the collision operator. And this collision operator can be seen as a rate of variation corresponding to a relaxation towards the equilibrium distribution. So sometimes a reasonable approximation taken for this is the f at equilibrium minus f divided by tau. Okay, so we talked about the LBM equation in the most simple way that I could explain it, but obviously it is a very complex topic, so there is deemed to be, complex mathematical aspects to deal with. Now, we will talk a bit about the algorithm, also not so much in detail, but to give you an overview of how that Lattice Boltzmann algorithm works, and then we'll finish with a small example. So let's talk quickly about space discretization. In the Lattice Boltzmann, the space to be discretized is not classical four-space dimension. So, and this is due to the distribution function that we saw, which is a function of position, speed, and time, but it's not possible to use a single spatial mesh on which time iteration has to be calculated. The mesh must correspond to a whole phase space discretization. So, to say that clearly, what this means is that the mesh must include geometrical nodes, but also speed nodes. And it's not easy to represent itself, but there is some kind of graphical representation in the next slide. And because of this, the mesh can't be represented in a completely free way because we have those speeds to represent as well. So if we take an example where we have a 2D problem in which the particles go from each node to another node, so there are 9 possibilities, right? So there are 9 speeds which will allow a particle to go from one node to another. So basically this kind of mesh has to be represented for this kind of 2D model. 9 speeds are sufficient, so they will provide sufficient isotropy to the model, and this is sufficient for weakly compressible fluid applications. But as soon as you want to go 3D or you want to have compressible application or other types, you might need to add more speed. So you have some model where you have 27 or much more than that speed vectors in your mesh. So you can imagine that that's a lot of computations. So this kind of mesh in the Lattice Boltzmann lingo is called the D2Q9 lattice. So that means that you have 2 spatial dimensions and 9 discrete velocities. Other type of LBM networks can be established, as I said, and generally for LBM lattice, so we call that DNQM, where you have n dimension, n spatial dimension, and m discrete speeds. Now, what's important to understand is that the black dots represent spatial nodes, but they're not occupied by only one particle, but by a certain number of particles that also depends on the local density. So what happens is that during one time step, a particle can only move to its nearest neighbor sites with one of the discrete speeds that are noted from 0 to 8. And the Fi's represent the number of particles that move with a discrete speed EI from a site containing n particles. And finally, we have Fi multiplied by n particles move at a certain speed EI. So once the particles, the groups of particles have moved, so we call that advection, the one from one neighboring site to the other, they will collide with other particles that arrive on the same site at the same time. So, that's some kind of bowling game, right? The particles go from one side to another and they enter in collision, and then, they either stay in their space or they go to the other. So that's a bit how it works if you simplify a lot. So in the LBM method, you have two-step, advection, and collision. So since now we know everything about the discretization of the phase space, we have to talk quickly about discrete form of the Boltzmann equation on a lattice of type D and Qm. So this equation takes generally the form that is written here. So I'm not going to read it, but you can see it here. So left term is a term of transport or advection, and Taylor development can highlight a form of Lagrangian transport. Term on the right is the collision operator, which corresponds to the rule that apply when two particles arrive at the same time on a geometric node. And here you have some kind of idea of how the LBM algorithm works in 5 steps. So first you have some kind of selection of a site. Then you have advection of incoming particle from a direct neighborhood. Then you have collision of the new set of particles that have just been advected. You have a post-collision rearrangement. And then you have a next site selection. So the LBM method is really working individually on sets of particles that are moving on a lattice like this with different speeds. And this is also why it's so good to calculate multi-physics types of behavior, because you can easily add new types of physics by added different way to calculate the collision operator, or I don't know exactly the details, but this is the way it works. And also, because the lattice is a grid, it can be quickly divided, and the interaction at each interface between the particle is what allows the parallel computation on GPU, which is much faster than with traditional nonlinear method to solve the Navier-Stokes equations. So now that we talk about the algorithm and everything, I still have 2 slides. So it's a simple example that Nicola has put together. So he has made his own very simple LBM solver, and he calculated the pressure pulse from which is an elementary benchmark in LBM domain. So it's more something about acoustics. So you take a domain which is initialized uniformly, except at the center when you have a small pressure shoot added to the average density, and you can see basically the particles that go from the middle and which are spreading around it with a certain spatial speed. So this is what you get as a density field after 0.5 millisecond of physical simulation time. And you can observe the initial density peak linear to pressure spreads to a slightly larger pressure wave followed by a refraction wave. So it's typical of that kind of test case, and it validates our implementation in a qualitative manner. And here are two plots which show a radial profile of the density at the beginning and after 0.5 millisecond. Okay, and that's all for this presentation. So I think it's already a lot of stuff. But if you want to go further on that and go a bit deeper on the way to calculate and implement the lattice Boltzmann, well, the good news is that there is another article on the blog, also written by Nicolas, who has really written a bit more about the kind of algorithm you can develop to make it work, and they are a nice example on it also. So you can go to this article and have a read at it. And of course, there are a lot of other stuff online, and probably in one of my next video, I'll be trying some of those open source LBM solver just to see how that works and what you can do with it, because it's always more interesting when it's actually applied to practical problems. So I hope you enjoyed this presentation. I hope it was useful. If it was, please leave it a thumbs up and let me know in the comment on the blog. I'm always happy to hear what you think about my videos and content. Thank you very much for watching this.